This video is to take you through part of the acidic environment focus area 2, mainly focusing on acidic oxides and something called LCP. This is the syllabus document. The things in red are things you'll be doing for your holiday work, usually around term 1 to term 2, focusing on acidic oxides in the atmosphere, looking at whether we should be concerned about acidic oxides in the atmosphere and the chemistry of how acidic oxides form and also affect the atmosphere in forming acid rain. The orange is an experiment we'll be doing. It's a soft drink equilibrium experiment. You're doing that in class, and you'll be revising moles calculations as well when you do that acidic oxides experiment in soft drink. What we're going to be focusing on this video though is acidic oxides of nonmetals and also basic oxides of metals, and something called Le Chatelier's principle, which I'll probably try not to say too often, and we'll probably summarize that as just LCP for short. But this section here, this green, is what we're going to be focusing on in this particular video. The first facts we're going to learn in this particular focus area are some very simple things. The first one is that oxides of metal are usually bases, and that's something you need to accept at this stage. Things like sodium oxide, potassium oxide and calcium oxide, they're actually soluble oxides in water, and they typically form hydroxides when they're dissolved in water. There are some metal oxides, such as magnesium oxide and some, which don't dissolve in water. However, they're still basic oxides. Metal oxides are basic, and the reason we call them basic oxides is because they react with acids to form salts, but they won't react with alkali solutions. There's some examples here: copper oxide, or copper 2 oxide I should say, and iron 3 oxide. They're metal oxides, and the fact we just learnt is the fact that metal oxides are bases. So we've got a base reacting with an acid in both cases. Base and acid, or acid plus base, is a neutralization reaction. We know they go to salt plus water. So you should pause the video and have a go at balancing both those equations, and we'll see the solutions to those equations very soon. The second fact you've got to learn in this video is the fact that oxides of nonmetals are generally acidic. And the reason why they're called acidic is because they react in water to form acidic solutions, and they also react with bases to form salts, or they do both. There's some examples of ones written here for you. Sulfur dioxide plus water turns into something called sulfuric acid, which is H2SO3, and that sulfuric acid can then react with oxygen to form sulfuric acid. There's an example of an acidic oxide. It's reacting with water to form an acidic solution. Another example is carbon dioxide reacts with water to form carbonic acid. Once again, here's an equation you can balance yourself, so pause the video and try balance that equation. And let's check the answers now. First of all, hopefully you balance those two metal reactions and have also managed to balance the carbonic acid reaction. But the key thing on this particular slide are these two facts. The things you need to know: oxides of metals are usually bases, and oxides of nonmetals are usually acidic. On to the next section of the notes. There are some oxides of nonmetals that aren't acidic though. Some of them do form neutral oxides. Some common neutral oxides are things like carbon monoxide and nitric oxide, and they don't form acidic oxides, they form neutral solutions. And one thing to note, a little thing that the HSC is picking up on, is the higher the oxidation number of the nonmetal in an oxide, the more likely it is to be acidic. We'll do some practice on that in a minute. There are some metal oxides that don't obey the basic oxide rule as well. Things like zinc, lead, aluminium, tin, in that region of the periodic table. Their oxides react with acids to form salts, but they also react with alkalis. And because they react with acids and alkalis, they'll be given a special name, and that name is amphoteric oxides. Now, it's very similar to the word you've heard before, amphiprotic. Amphiprotic means it can be a proton donor and a proton acceptor, i.e. act as an acid or a base. These don't act as acids or bases, they react with acids and bases, therefore they're called amphoteric oxides. And because we just learnt that metal oxides are typically basic, there's a small range of metals in the middle of the periodic table which are amphoteric. We learnt that generally non-metal oxides are acidic. There's a trend across the periodic table which goes from basic to amphoteric in the middle to acidic as you move from left to right across the table. That's an important fact to learn. So I'll bring that along. I've just highlighted some key facts here. The first key fact here is there are some non-metal oxides that are neutral. The next key fact is that the higher the oxidation number of the non-metal in an oxide, the more likely it is to be acidic. You need to know there are a small group of amphoteric metal oxides, and that's just a summary of the trends across the table. Left to right, it goes from basic to amphoteric to acidic oxides. And you've got your first activity to do on this sheet. There's a periodic table on your booklet. You've got to choose 4 different colors. I recommend red for acids, blue for bases, pink for amphoteric, and some other color for those which don't form oxides. So Colour in the elements that form acidic oxides red, the ones that form basic oxides blue, the amphoteric pink or some other in-between colour, and those which don't form any oxides, one colour. You could also use yellow like I've done up here for any neutral oxide formers on the periodic table. So have a go at that, pause the video, and then we'll check your answers in just a second. So the table should look like this. Hopefully you've got some sort of key. My key was acidic oxides red, basic blue, amphoteric pink. I've gone yellow for no oxides, and I've just gone no colour at all for neutral. I think that's what I decided with in the end, and that's how it went. So hydrogen oxide is water, is a neutral substance. There are some carbon and there are some nitrogen oxides which are neutral, but they also form acidic oxides, so therefore also red. The noble gases don't form any oxides, so I've gone with yellow for them. Oxygen doesn't form any oxides apart from just O2 molecules, and therefore it doesn't really form an oxide. I've gone with yellow for that. But all these metal oxides here should be blue. There's those small range. You've got aluminium, you've got zinc, you've got tin, and you've got lead down here. They form those amphoteric oxides, and all the non-metals in here form acidic oxides. And then there's that second question there, the trend. The trend goes from basic, amphoteric, to acidic, to no oxides as you go from left to right across the periodic table. There's a whole range of review questions here on page 4 of your booklet to go through. I recommend you pause the video, have a go at those questions, and then you can unpause the video and check your answers. Let's just quickly go through those answers. First of all, it says here that basic oxides will dissolve in water to form hydroxide. So obviously magnesium oxide plus water turns to magnesium hydroxide, and there's the balanced equation for that. Don't forget to use the cross method whenever you find the formula of an ionic compound. It asks here that basic oxides react with acids to form water and a salt. So you've got magnesium oxide with hydrochloric acid. It's acid plus base because salt plus water. And there's the balanced chemical equation. Once again, make sure you've used the cross method to get the formula of your ionic compounds correct. Otherwise, you won't be able to balance things properly. It's got a definition of amphoteric oxide, an oxide that reacts with both acids and bases. And this one here is focusing on oxidation numbers. It says calculate the oxidation state of nitrogen in NO2, NO, and N2O, and outline how oxidation number of a non-metal oxide affects the acidity of the oxide. Hopefully you managed to use your skills from Focus 4 of production materials to realise that if oxygen is -2 in all compounds, that nitrogen there must be +4, that one must be +2, that one must be +1, and that's what those answers down there. NO2 is the most acidic of those nitrogen oxides because the higher the oxidation number of the non-metal, the more acidic the oxide is. And then this last question, which one's going to be more acidic? Will it be Cl2O or Cl2O7? I calculated the oxidation number of chlorine in both. In the first one it was +1, in the second one it was actually +7, and therefore I said Cl2O7 is the more acidic oxide because the chlorine has a higher oxidation number. At this stage of the course, it's very important you can balance chemical equations, particularly those involving acids. So there's a series here to balance. Please make sure you balance them, and then you can check the next. We'll pause the video and then play it again and check your answers. The answers are here. Sorry about the handwriting, but if you've balanced them, you should be able to just quickly check if you've got them balanced correctly. If you've made any mistakes in these ones, please make sure you go back and do them again or get some support, because being able to balance chemical equations is a critical skill. Same thing here. Here's some more equations, this time with basic oxides reacting with acids. Please have a go at these. Pause the video and have a go at them. Particularly focus on the ones that have transition metal ions in them. They can be quite challenging. Note the valency of the metal won't change in the reaction. So if it's, for example, vanadium 5 in the reactants, it'll be vanadium 5 something in the products as well. So pause the video, have a go at these, and then check your answers in a minute. And once again, you can check your answers. Once again, they're all handwritten, but you should be able to see if you've balanced them correctly or not. We've just finished looking at the trends of oxides across the periodic table, from basic to amphoteric to acidic to no oxides as you go from left to right across the periodic table. We're now about to start looking at a next concept called equilibrium, and one of the big focuses on this whole section is looking at this thing called equilibrium. We first looked at this way back in year 11, looked at reactions that can go forwards and backwards. We're going to look at it in much more detail now. Now before you begin, it's very important to do some revision on the basics of equilibrium and rates of reaction. That's in your surfing book. It's very important you do that now before you go ahead to make sure you've got a good solid understanding of equilibrium before we start this. Otherwise this video won't make much sense. Okay, assuming you've done that revision on the surfing set, let's just do a quick recap on equilibrium. The key idea of equilibrium is that some reactions are irreversible. There are some reactions that aren't in equilibrium. They go in one direction. The reactants react, form the products, and that's it. Some examples of things like burning magnesium, metal plus acid reactions. Also, as we're going to see in a second, one example that is strong acid ionizations. We know that strong acids completely ionize, and those weak conjugate bases or very weak conjugate bases that form don't reaccept protons and turn back into the acid again. So we say those reactions go to completion. There's a complete conversion of reactions to products when stoichiometric amounts are mixed. And what that means in terms of stoichiometric amounts, as we learned in titrations, it means we've added exactly enough of each reactant so that each react and no reactants remain in the system at the end. However, some reactions are reversible, meaning the forward and reverse reactions both occur. There's an example here. You don't need to learn this example, but the key thing is to know that in these reactions, the reaction occurs simultaneously in both directions. It's called a reversible reaction. So in this case, what it means is as iron is reacting with water, somewhere else in the reaction mix, some of the iron oxide is there reacting with hydrogen to turn back into iron and water again. So the reaction is going in both ways. Now, note for a reversible or equilibrium reaction, we draw the double arrow to show that it's going in both directions. And reversible reactions eventually come to a state of equilibrium. After reacting for a while forwards and backs, eventually what happens is the rate of forward reaction equals the rate of reverse reaction, and even though the reaction continues, the amount of products and amount of reaction stays constant because the rate of reaction is the same in both directions. So let's just highlight some of the key points from that page. The critical thing, make sure you've done your revision. We did an example here. We talked about the fact that strong acid ionizations is an example of a reaction that doesn't happen in equilibrium. Example, 100% conversion of strong acids, i.e. 100% ionization. We learned that some reactions are reversible, meaning both the forward and reverse reactions occur. And an example of that, which we didn't talk about, was weak acid ionization. We know that weak acids only partially ionize, so a weak acid forms a weak conjugate base in equilibrium with water and hydronium ions, and that weak conjugate base will then reform the acid again. So weak acid ionization is an example of an equilibrium or reversible reactions, and we learned that reversible reactions come to a state of equilibrium. So what does equilibrium actually mean? Well, equilibrium is used to describe a reversible reaction in a closed system, when that means no energy or matter is entering or leaving, which has reached a point where the rate of forward reaction equals the rate of reverse reaction. And that means because the rate of forward reaction is equal to the rate of reverse reaction, the concentrations of products and reactants remains constant at that time. So you don't see any macroscopic change in the properties. So just highlighting the most important points there. Equilibrium is defined as a reversible reaction in a closed system where these two things are true, and you have to know these things. The rate of forward reaction is equal to the rate of reverse reaction, and the concentrations of products and reactants remains constant. So just as once again a recap for you, let's have a look at some of these in graphical terms. So it's going to be two graphs drawn on the space of your page, side by side, one concentration versus time, and one rate of reaction versus time. If ever you have a reaction, you always start off with some reactants. You can't start off with no reactants, the reaction won't occur. You start off with some reactants, but because they react, their concentration drops over time. And this becoming straight represents equilibrium. So the amount of the reaction concentration will decrease, and then come to some constant amount in an equilibrium reaction. Because reactants are reacting, that means we're making product. We start with no product, but the amount of product is actually increasing over time until eventually you reach a constant concentration of product. The point at which, the point at which the concentrations of both reactant and product become constant over time, that's called the position of equilibrium, or the time that equilibrium was reached. You can mark that on your diagram as well. And the key thing to note is at equilibrium, the concentration of reactants and products remain constant. But the key thing is to note there's a gap between them, there's a difference between them. You don't have to have the reactants and products at the same concentration, just that their concentrations remain constant. And depending on the, for example, percent ionization of the acid or the degree of reaction, we'll get different amounts of reactants and products at the equilibrium point. The last thing to note is that the rate of reaction is proportional to the gradient. It's not equal to the gradient. You can't do your calculus on this and actually calculate the rate of reaction, but the rate of reaction is proportional to the gradient. And knowing that, we can use that to do a rate versus time graph with an equilibrium reaction. So first of all, it's clear the gradient is very high at the start over here of the reaction, and it drops to a low gradient as it comes to equilibrium. So we can draw that on the rate of reaction curve. The reaction rate starts high and then drops over time. That's the rate of forward reaction. Similarly, the reverse reaction starts to pick up. At the very start, we've got almost no products, and therefore it's very hard for the products to actually react and go back to the reverse reaction. But over time, there are more and more products, and therefore the rate of reverse reaction grows. And so you get these two curves here, one representing the rate of forward reaction, one representing the rate of reverse reaction. And just like we said up the top here, Its equilibrium is when the rate of forward reaction is equal to the rate of reverse reaction. So that point at which those two rates become the same is the point of equilibrium. So these are two graphs, both representing the same equilibrium, just looking at different things. In terms of concentration, equilibrium is when the concentrations start to remain constant over time. In terms of rate, though, the equilibrium occurs when the rates are the same. The rate of forward reaction equals the rate of reverse reaction. And just some notes here, the forward reaction rate decreases with time as the concentration of reactants decreases. The reverse reaction rate increases with time as the concentration of products increases, but at equilibrium the rate of forward reaction is equal to the rate of reverse reaction. So these two graphs represent exactly the same thing, just with different axes, showing you different ways of looking at equilibrium. And it's time for some revision. Here's a good chance to stop and do some revision of what you just learned about equilibrium. Surfing set 5, questions 2 to 4 and 6 to 8. Now you've revised equilibrium and learned a bit more about equilibrium, there's a chance to learn this new thing, Le Chatelet's principle. We're going to call it LCP from now on. This actual phrase is actually in the HSC syllabus. You probably should know it. In an extended response, you probably should write it first, but I'll definitely put that in brackets, LCP, after writing that out, and then call it LCP from that point onwards. In the previous part of the video, we just looked at the fact that at equilibrium, we get to a point where the rate of forward reaction equals the rate of reverse reaction, and because of that, the concentrations of reactants and concentrations of products remain constant at that point in time. However, if you change the conditions of equilibrium, if you change the temperature, if you change the pressure, if you add some chemicals, if you take some chemicals away, you've just affected the equilibrium. And that means the rate of forward and reverse reaction will be altered, and they will no longer be equal. And depending on what you've done to the reaction, that either means either the forward or reverse reaction direction will be higher or lower, and therefore a new position of equilibrium will be established. If you, for example, increase the rate of forward reaction, that means more reactants will turn into more products, and therefore you'll change that position of equilibrium. And that's detailed in Le Chatelet's principle to determine exactly what happens when you affect an equilibrium. That's what Le Chatelet's principle is all about. And it states, if the conditions of an equilibrium system are changed, the position of equilibrium will shift to counteract the changes made, and a new equilibrium will be established. And that's the key thing here. Whatever you do to an equilibrium, the equilibrium system will try and counteract your changes. If you heat the equilibrium up, it'll try and cool itself down. If you add pressure, it'll try and release the pressure. If you add a chemical, it'll try and consume that chemical. Whatever you do to the equilibrium will shift to counteract your changes, and that means a new equilibrium will be established. And there are three things you can do to affect equilibrium: that are change the temperature, change the pressure, or change the concentration. We're going to look at each one of those in turn to see how they affect equilibrium. So the first one I'm going to look at in detail is temperature. For any reversible reaction, in this case just a general thing, A plus B in equilibrium with C plus D, if the forward reaction is exothermic, by definition the reverse reaction must be endothermic. So, i.e., if A plus B turns into C plus D, if that reaction is exothermic, then therefore C plus D turning into A plus B must be endothermic. We're going to draw some pictures just to reinforce this and to show why that is the case. So first of all, you're going to be drawing two graphs, one here and one over here, side by side. But a little thing over here, just to try to get our brains thinking about how this works. If this reaction A plus B goes C plus D is exothermic, that means it releases heat. We could write that as A plus B turns into C plus D plus heat. And we're just going to pretend like heat is another products in the reaction. Similarly, if C plus D turns to A plus B is endothermic, that means it has to absorb heat. So we can pretend that heat is one of the reactants. And that process, or that idea of doing things that way, helps some students understand equilibrium and how Le Chatelet's principle works a little bit better. So what we're going to do is these enthalpy diagrams, as I said before. We're going to draw the forward reaction diagram first. Don't forget, enthalpy diagram is enthalpy, H, versus time. And we're going to start off with our reactants, A plus B, and they've got a certain amount of chemical enthalpy stored inside their bonds. Now, in any reaction, enthalpy diagrams, don't forget there's an activation energy. Any reaction has to go over a hump. But we said it's an exothermic reaction, which means heat has been released, which means C plus D must have less enthalpy. They've got lower enthalpy than A plus B. Now, if we reverse that reaction, and we're starting off with C plus D, the reverse reaction graph's going to look like this. We're starting off with those same chemicals C plus D with low enthalpy. We're trying to turn them into A plus B, but A plus B have high enthalpy. And therefore we've got to add a whole lot extra energy, including the activation energy, and that's going to drop down to the A plus B level. And so if the forward reaction looks like this, the reverse reaction is going to look like that. It's just the mirror image, obviously. And by that way, same token, we can see that in this forward reaction, delta H is negative. We've started off with high enthalpy and we've dropped to low enthalpy, so delta H is negative. For the reverse reaction, we're starting with low enthalpy and we're finishing with high enthalpy, and therefore that is an endothermic reaction because delta H is positive. Similarly, because we're dropping enthalpy, that energy has to go somewhere. That's released as heat. And the same thing, the reverse reaction, because it's endothermic, the enthalpy is going up. That enthalpy has to come from somewhere. That means heat energy must come in. So that just shows you that if the forward reaction is exothermic, like this forward reaction is releasing heat, then the reverse reaction has to be endothermic and absorb heat. And now that's been revised, we can actually start looking at how that applies to Le Chatelier's principle, or LCP, and equilibrium diagrams. If the temperature of an equilibrium system is changed, then by Le Chatelier's principle, the position of equilibrium will move to counteract the change in temperature. So we're just rewording LCP here to talk about temperature in specific detail. So if an equilibrium reaction is heated, just have a think for a minute, if you heat a reaction, how does that apply to that statement? We've said by LCP, the equilibrium will shift to counteract the change. So what's the counteraction to heating? In my mind, it's cooling. So let's have a look at how that works. So if an equilibrium reaction is heated, the endothermic reaction becomes favored because endothermic reactions absorb the heat or counteract the change. Similarly, if you cool an equilibrium reaction, something's going to happen from Le Chatelier's principle to counteract that change. Counteracting cooling is obviously heating, so you've got to think to yourself, what process or what reaction pathway produces heat? Well, and the answer to that is if an equilibrium reaction is cooled, the exothermic reaction becomes favored because that acts to raise the heat. So you're seeing how Le Chatelier's principle, or LCP, the equilibrium shifts to counteract the change that's being made. The best way to learn this though is by doing some examples. Let's look at a few examples from your notes. So first example A1, is two carbon monoxide gas molecules are in equilibrium with carbon dioxide gas and solid carbon. Now delta H is negative, which means exothermic, so we could rewrite that equation, as we said before, as two carbon monoxide molecules in equilibrium with carbon dioxide plus carbon solid plus heat, because it's releasing heat. Heat is like a product in this reaction. So the questions are, identify which way the reaction will proceed if it's heated or cooled. So let's just think for a second. If it's heated, LCP says the equilibrium will oppose the change. In this case, we've just heated it, so that means equilibrium has to shift to cool the reaction and remove heat. So now you've got to ask yourself your question, which direction of the reaction removes heat? And hopefully you answered that the endothermic reaction removes the heat, and therefore by Le Chatelier's principle, if you've heated the reaction, it'll shift to the left, which is the endothermic reaction, to remove or absorb that heat. Now look at the second question here. If you cool the reaction, what's going to happen? Well, by LCP, once again, the equilibrium will shift, or equilibrium will oppose the change, so it will shift to oppose the cooling, which means adding heat. So you've got to ask yourself the question, which direction of the reaction adds heat? As we've drawn on the diagram above, by LCP, the equilibrium will shift to the right, which is the exothermic reaction, to add heat. So in both these cases, we've seen the equilibrium will shift to counteract the change. On to the second question, on to A2. It says, if you cool the following equilibrium, which is this one here, what will be the result? Now this one here is PCl5 goes to PCl3 plus Cl2 gas, and it's got delta H is positive 95 kilojoules per mole. Now don't forget, if you get a positive delta H value, that means the reaction is endothermic. Heat is like one of the reactants. So we could rewrite that reaction like this, PCl5 plus heat goes to there. And the answer to this question is, if you cool this reaction, by LCP, the equilibrium will shift to counteract the change and a new equilibrium will be established. Thus cooling favours the exothermic reaction, as this will act to raise the heat. So in this case, if you cool this equilibrium, the equilibrium is going to shift this way to try and produce heat to counteract the change you made. Looking at the third example on temperature, and the last example on temperature is A3, the Haber process for producing ammonia uses the following reaction. It's 3 hydrogen gas molecules react with 1 nitrogen molecule to produce 2 ammonia molecules. And that's delta H minus 92 kilojoules per mole, which means it is going to be an exothermic reaction. So if I skip forward one, we can write that down as 3H2 plus N2 in equilibrium with 2 ammonia molecules plus heat, because it's exothermic reaction. And the question is, if you wanted to increase the amount of ammonia produced, should you heat or cool? This is a good chance to pause the video and think about what you've written down and think of what you've learned so far. If you want to make the reaction go to the right, which means produce more ammonia, should you heat it up or should you cool it down? Don't forget, equilibrium will shift to counteract the change you made. So pause the video, have a think about the answer, and then check your answer in a second. So if you want to increase the amount of ammonia, you need to favour the forward or the exothermic reaction. Thus, by the Shetler's principle, LCP, the reaction needs to be cooled, because if we cool the reaction, it's going to try and heat up the reaction. The way it heats up the reaction is shifting to the right, which is what we wanted it to do. So if you actually want to make more ammonia in this situation, you cool it down, therefore more hydrogen and nitrogen react to produce more ammonia, because that's the exothermic reaction direction. Now we're going to start drawing some equilibrium diagrams here. This is what this little graph here is for, to show how equilibrium diagrams work. We're going to do a lot more of them in the chemical monitoring management topic. This is our introduction to them right now. So the first thing you've got to do is realize you're reacting hydrogen, nitrogen and ammonia together. And this is for this example A3 here. Now clearly you want 3 hydrogens reacting with 1 nitrogen to produce 2 ammonias, and therefore in your initial reaction mix you're going to have more hydrogen than nitrogen. So all you need to do is just arbitrarily choose 3 points on your graph. Obviously ammonia will start off at 0 because it hasn't been produced yet. Hydrogen will be higher than nitrogen because that's where we're starting from. It's our starting points. The next thing you do is realize it's a 3 to 1 to 2 ratio. For every 3 hydrogens that react, 1 nitrogen will react and 2 ammonias will react. This dotted line here represents the first equilibrium. So what you do is think, okay, I know the reaction is going to start. I'm starting off with all hydrogen and nitrogen. I'm producing ammonia. It's going to start to produce ammonia, which means by definition some of the nitrogen and hydrogen has to drop. So what I do is I just pick some random point, well not random, I just pick a point on this dotted line which represents my first equilibrium that is lower. It's a little bit lower down than nitrogen. The nitrogen is going to decrease, and I call that 1. I call that unit 1. Now, if I'm trying to think about where the hydrogen is going to be, I know it's a 3 to 1 to 2 reaction. So however much nitrogen drops by, the hydrogen has to drop by 3 times as much. So the next thing I do on my graph is I put a dot for hydrogen, which is approximately 3 times lower. It doesn't have to be perfectly measured out. This is just an approximation diagram, but you've got to make it as reasonable as possible. So if nitrogen's dropped by 1 unit, hydrogen's got to drop by 3 units, and because we're producing ammonia, ammonia has to go up by 2 units for that 3 to 1 to 2 ratio. Once you've got those 3 points here, here and here marked on your equilibrium spot, what you do next is you start drawing the curves in. So first of all, the reaction starts off fast, therefore the gradient starts off big, and then it drops to a 0 gradient at equilibrium. I'll do the next one for hydrogen. The reaction starts off fast, a nice high gradient, and then drops off to equilibrium. There's a nice straight lines here for equilibrium. And last but not least, I drew my ammonia. Once again, the reaction starts off fast, a high gradient, and then drops to 0 at equilibrium. So my 3 gases, hydrogen, nitrogen, and ammonia, have reached equilibrium, and now it's time to start thinking about what happens if we actually try and cool this reaction. So I've later on here, equilibrium reached at that time. That's the time at which they've reached equilibrium, at the time at which all 3 came to a constant concentration. The concentrations aren't the same, the concentrations aren't equal, but their concentrations are remaining constant. The next thing I do is I put a new dashed line in. This is where my change happened. I'm going to say the system was cooled at this point. I'm going to try to draw the graph. What's going to happen to my graph once I cool the system? Well, as we set up here, by the LCP, because I've cooled the system, the exothermic reaction is favoured, and that means the ammonia concentration goes up, but the nitrogen and hydrogen concentrations will go down stoichiometrically. So I mark on somewhere over here where I think the new equilibrium is going to be. Once again, I just said nitrogen is going to go down, so I've just chosen a point. This blue spot represents some value less than the original nitrogen value. Now I call that drop in nitrogen, that was my 1 unit. Hydrogen has to drop by 3 times as much, so I've drawn my hydrogen dot 3 times lower than where the hydrogen originally started from. And by the same token, the ammonia, it started here, it's got to go up by relatively 2 units. So nitrogen's dropped by 1 unit, hydrogen's dropped by 3 units, and ammonia's gone up by 2 units. Once I've got those 3 spots in, the next thing I do is start drawing the curves. There is my nitrogen, it is curved down, and that should have been a straight line, just hard to draw with the pen on the screen sometimes. Hydrogen's dropped as well to that spot there, and the ammonia's gone up to that spot there. So I can now draw in, this is my new position of equilibrium. Okay, I'm going to say new equilibrium reached. The concentrations have all changed because I've affected the equilibrium. This is what LCP is all about. If I do something that affects the equilibrium, the position of equilibrium, I'll get a new equilibrium. This equilibrium is different to the previous equilibrium with different concentrations of reactants and products in my new equilibrium. One little thing to note here, if you look at this distance here, this took a lot longer to reach this second equilibrium than the first time, and that's just a way of showing the fact that we know as good chemists that we've just decreased the temperature, we've cooled the system, and reaction rates drop as we cool the temperature. Therefore, the time to react will take a lot longer. And that's our first introduction to equilibrium curves. The next example is looking at volume changes, the second thing that can affect equilibrium. And this is volume change for reactions involving a gas phase. Volume change only affects things if they're in the gas phase. And an important thing to know about gases is that pressure and volume are inversely proportional. Pressure is proportional to 1 on the volume. All that means is if you decrease the volume of a container, if you squash gas into a smaller container, the gas pressure inside increases. And there's a few ways of decreasing volume. You can actually physically just compress the volume of the container, or you can get the gas from the container and pump it into a lower volume container. So what you need to know is as the volume of a container is increased, the gas pressure inside decreases. As the volume of a container is decreased, the gas pressure inside increases. And a good way to think about that is something you might have seen in everyday life is a syringe. So we look here, this is a little diagrams to put in. If you've got syringe for some reason squashed into some gas squashed into a syringe, the end is sealed off. We know those sliding ends are also airtight as well. We'll get our plunger here, and we've got some gas inside this syringe. It's got a set volume, volume 1, and it's currently at a pressure I'm just going to call P1. If you happen to push that plunger in, that means you're squashing those gas particles much, much closer in together. So what you've done is you decrease the volume. You've got volume 2 here, which is a bit lower than the previous volume, but because the gas molecules are all squashed in, that means that pressure, P2, is higher than the original pressure. So what that means is if you decrease the volume of the gas, the pressure will go up. Similarly, down here, in this situation, the plunger has been pulled outwards. That's increased the volume available for the gas. So volume 3 is actually bigger than volume 1. However, because you made the volume available bigger, the gas molecules are more spread out. You've got a new pressure, P3 now, and P3 is less than the original pressure. So what that's showing is if you increase the volume available to a gas, its gas pressure will go down. And that's what these two key things are here. We've got the fact that pressure is proportional to 1 on volume. What that means is if you decrease the volume of a container, the gas pressure inside increases. If you increase the volume of a container, the gas pressure inside decreases.